Hello guys, how are you? Turns out I forgot to do one past paper, so that's very funny. This past paper is, let me just check what it is. It is, just a second to see where I have it. This past paper is 9702, paper 23, May, June 2022. So this is what this is. I gave the wrong past paper for one of the previous, but this is another past paper we have, by the way. So let me just do it right now. I'm so sorry, I forgot to mention it. A laser emits a beam of electromagnetic waves of this frequency. So show that the wavelength of the waves is this much. How do we show that the wavelength of the waves is this much? Very simply, we know that the equation that relates wavelength and frequency is that lambda is equal to the speed over the frequency. So the speed of light in vacuum is 3 times 10 to the power of 8. Divided by 3.7 times 10 to the power of 15 hertz. You will put it on the calculator and you are supposed to get an answer of, it is gonna be approximately 8.1 times 10 to the power of minus 8 watt meters. Perfect. Now state the region of the electromagnetic spectrum. This, if you were to change it to nanometers, it would become 80 nanometers. So it is in the range, or not 80, 81 nanometers, my bad. So it is in the range of which of the following radiations? It's of the range of ultraviolet radiation. Now we move on to part 3. What does it say in part 3? It says that the beam from the laser now passes through a diffraction grating with 2,400 lines per millimeter. A detector sensitive to the waves emitted by the laser is moved through an arc of 180 degrees in order to deflect the maxima produced by the waves passing through the grating as shown in the figure below. They want us to calculate the number of maxima detected as the detector moves through 180 degrees as the line shown in figure 5.2 and show our working. So very simply, if we go back up, we notice that they gave us what? They gave us n, right? They gave us n, and it is in millimeter. So how do we find d from n? D is equal to 1 over n. Of course, 1 needs to be in meters, so you will divide by 1,000. So it's gonna be 1 divided by 1,000 over 2,400 lines, and this will give us an answer of what? This will give us an answer of 4.2 times 10 to the power of minus 7. Okay, so this is how we get d from it. So they want d? No, they want the number of maxima detected. So how do we find the number of maxima detected? The number of maxima, denoted by n, we can find it very simply by using the equation d sine theta equals m lambda. We have lambda, which is 8.1 times 10 to the power of minus 8, and we have what we have d, which is 4.2 times 10 to the power of minus 7. And for theta, in this scenario, because they want the maximum, we will replace it by 90. So 4.2 times 10 to the power of minus 7 times sine 90 is equal to m times 8.1 times 10 to the power of minus 8. So that means m is equal to 4.2 times 10 to the power of minus 7 times sine 90 over what? Over 8.1 times 10 to the power of minus 8. And we will get our answer to be what? To be approximately 5.1. Okay, so the number of maxima detected is from up 5. You always take the smallest whole number. So 5, and also from down there's gonna be 5. And as well, we do not forget that we are dealing with what? We are dealing with the bright fringes, so we will not forget about the central brightness, which is 1. So you add them all together, 5 plus 1 plus 5, you will get the number of maxima detected to be what? To be 11. Now, part IV, the laser is now replaced with one that emits electromagnetic waves with a wavelength of 300 nanometers. So what did we do to the wavelength? We increased the wavelength. They said, explain without calculation what happens to the number of maxima now detected. Okay, assume that the detector is also sensitive to the wavelength. So we know that the wavelength increases, right? And because the wavelength increases, we know, based on the proportionality rule, we know that it's d sine theta equals m lambda. M and lambda are on the same side of the equation. So as lambda increases, m is going to decrease. So we can say, so the number of maxima will decrease. So this is it for this past paper. It's very small, very short. Sorry that I forgot it. Hopefully you guys will see it in time, and thank you guys for watching. I hope you enjoyed and have a wonderful day.